All right, guys. So, what we are going to show you first today, it's about the introduction to thermodynamics. All right, and we'll just do like a discussion and things like how familiar you guys with the concepts that we are about to introduce to you. So, the main portion that we are trying to do first is talking about what is temperature. Okay, I think you guys familiar with this for sure. And then I think maybe the key one that we're going to need a lot is heat. I don't know what is, your perception about heat, but what we're trying to do here is we try to bring in the heat and then, put slap on some physics principle and things that we can sort of like do the calculation with. And eventually you're going to arrive at thermodynamics, okay, toward the end. So what we're going to do is we're just gonna, define what kind of like what's importance of having thermodynamics. Why do we need this subject at all, and what's kind of thermodynamic system that we have to deal with. All right, and we're going to properly define temperature. What does temperature mean? Okay, and we're going to, the weirdest stuff is starting right away, is introducing to you the zeroth law of thermodynamics. I know. All right, this kind of thing only physicists can do. All right, why introduce like zeroth law. Right? Okay, and I think we have enough time to talk about a little bit of thermal expansion. All right, and once we're done with that, and the rest, we can talk about this on Wednesday. Okay, sounds cool. All right. So first of all, guys, just asking, right? Just for fun. I don't know if you guys sort of like would like to think in this line of thought at all. Why do we need thermodynamics? Or you may be even asking like, why do we need physics? All right, the reason is easy for physics because it's a fundamental of everything. So we need physics because that's how we understand how nature works, right? That's the whole thing. However, when we go a little bit deeper into this topic over here, thermodynamic system, why do we need this? What is this? What is thermodynamic system? So let me start by asking you a very simple question. How many oxygen molecules are there in your room right now? Just, it doesn't have to be a room. You could be in like open air, but let's say around you, let's say, around your environment, how many oxygen molecules, including the one that you just sort of like breathe in, whatever, just approximate. All right, we don't know exactly, but what kind of numbers that you can come up with. Look around, how many oxygen running around. What do you think? Any participation here? Probably more than 10. Of course, it has to be more than 10. Okay. 10 is kind of like, it's kind of like, it's kind of small number. Okay. All right. Definitely more than 10. Yeah. Any more? More than 11. Come on. Okay, guys. All right. Don't go for 12 or 13. All right. So we come up with like an order of magnitude, guys. Sort of like what order of magnitude we talking about? Like 100,000. Here we go. Somebody just hit with the big number there. It's 10 to the 25th. Yeah, that's 10 to the 25th order. And that is a very good number. Why? Because you guys still remember Avogadro number? Yeah, it's like 6.02 times 10 to the 23rd, on and on, right? So we are dealing with that kind of numbers. It's like if you came from like chemistry, it's like you have like 1 mole of gas. Okay, so that's one Avogadro numbers. So we are dealing with like million, and millions molecules or atoms or whatever. So now the second question, guys. All right, so the number is good. I want this. Can you guys come up with the total kinetic energy of this oxygen molecule? So if I asking you, hey, I would like to get the total amount of the kinetic energy of those oxygen that's running around, and everyone know what done, we got it, 1/2 mv squared. We just learned it from Newtonian physics. But okay, the formula is good, everything is good. There's no doubt about it. But then you have to sum all those million value, which you guys probably can say about that. I can do it because I have like a supercomputer. I can calculate for you. That's not the end of the whole story, because question is, how can you figure out the velocity of those oxygen molecule running? All right, you might have like a super fast camera or whatever, but the thing is, no matter how you want to do it, with that amount of number, you cannot. It's not practical. Even though in principle you can, it might take like, million years to do it. But anyway, the thing is, it's not attainable in real life. You cannot. Okay. And don't forget, those oxygen molecules knocking each other. So even though you can measure the speed of one molecule, but you don't know what will happen in the next second or next millisecond. It might just knock, the wall, change the direction, knock with its friends, knock with its neighboring atoms or whatever. So you cannot get a real time velocity or the speed of all the oxygen molecule in the room, right? So here comes my final question. So is this number possible to calculate at all? The total kinetic energy of the oxygen molecule in the room. So if I just said, but Ajahn, I cannot do it because, the limitation is the numbers, or the limitation is the device to detect something million values at the same time. It's not doable in real life. So is this the unanswerable? Is that a word? Okay. You said you can, but not accurate, right? Okay. That's a very good choice of word, actually. The answer is the accuracy is one thing, but there is something that you can actually get close to, even though it might not be perfectly 100% because you don't know everything 100% anyway. So it turns out, guys, you have to think of statistic now. Whoa, cool. Because when you're dealing with something like million of stuff, you don't know the final answer for sure. Like, let's say, hey, guys, what is the average height of Thai population, for example? Of course, you're not going to be able to, measure the height of every single person in the country and then come up with the final value of the average, right? You have to come up with like statistical method. You do some sampling, you do some, statistical inference, try to use your sample mean to approximate the population means, blah, blah, blah. But at least you have some way, right, to get to that. And that's usually through statistics, right? And it turns out, guys, the nature is crazy. Yeah, it has statistics as well. That velocity that we don't want to measure directly has statistic. And because the statistic based on the fundamental principle from Newtonian physics. And now you have the population of million. So this is like so close to the theoretical setup that you learn from statistics. You love it. All right, this is good. And it turns out, guys, you will learn here that eventually this total kinetic energy of those molecules that running around relate to the temperature. Whoa. Isn't that cool? No. So what my point is this, the reason that we need thermodynamic system is we don't have enough resource, even though we know Newton's is correct, Newtonian physics is good, but we don't have enough resource to do everything according to Newtonian physics straightforwardly. You cannot just do direct hits like, hey, I'm going to measure the velocity and I'm going to put in the expression 1/2 mv square and I'm going to sum them up. No, you cannot. But we can, turns out, answer this question simply by take a look at the temperature. Whoa. And now once this temperature changes, so you can have like a delta, the change of the temperature. Now you start to see the dynamics of this. So things that has some changes, which is a dynamic, that related to temperature, related to, some thermal aspect of the system. And inside the system, it's composed of like million of tiny stuff. That is your thermodynamic system, guys. And that's what my take on this one.
Okay.
Maybe it's like not a proper way of introducing thermodynamic system, but the idea is this. The reason we need this thermodynamics, because Newtonian physics cannot take us to that level of detail. Okay, it just, even though it's correct, but the numbers is just enormous. We cannot deal with that. Okay, so how do we deal with this? it turns out we only turn our attention and then we're going to deal with temperature. Cool. So knowing temperature, you knowing total kinetic energy of your system. First time I'm seeing this is like a whoosh, it's just like blow my mind a little bit because amazing. Yeah, it's amazing that temperature is the only key parameter that allow you to understand the whole population, right? So I mean, if you can imagine about temperature, it's the same thing as this is a parameter that characterizes the whole population. Yeah, it can be distribution, it can be like a curve or whatever, but the average, that's right on the temperature. The temperature give you the average. That's my take on it. So the way that you can measure the temperature, of course, you use thermometer. But now because we understand that temperature eventually lead to the energy of the system. So no doubt, every time that you put system one and system two in contact, now they're interacting, and then there is a chance that you can transfer those energy. And because we know the temperature links directly to the level of energy. So every time that you put two together, for example, thermometer, if you want to measure the temperature of this liquid over here, you put them in contact. See, they are in contact. And if they are at the different temperature, they're going to somehow exchange until eventually you reach some equilibrium. And because in this type of equilibrium is the equilibrium that's based on temperature. So it's a thermal equilibrium. It's not like mechanical equilibrium anymore. Cool? All right. So now we have, I'm just throwing some more technical terms to you. It's not technical term, but it's just the words that we use describing thermodynamic system: thermal equilibrium, thermal contact, temperature, total kinetic energy of the system. Cool. All right, keep going. All right, so what you have over here is now, so it seems like the temperature will be the parameter that allow you to tell if two systems are in equilibrium or not. Okay, so here comes the zeroth law. If object A and object B are separately in thermal equilibrium with the third object C, then it's guaranteed that A and B are in thermal contact, in thermal equilibrium as well. Done. Wow. There's nothing here. Everyone just like, Dan, actually object C is nothing more than just like thermometer here, right? This is thermometer. So the reason this one is like thermometer, because when you put thermometer and then you measure the temperature, and if it's like say 30 degree and you put that thermometer into another system and it's 30 degree, well, okay, Ajahn, they both at the same temperature. So if you put those two systems together, they are already in equilibrium. Cool, done. All right, you guys probably wondering like, why? And because physicists want a complete picture of everything, so they want this to be like the fundamental laws before every other laws. But because they have already defined the first, the second, and the third law already, they don't know where to put it, so they put it in the zeroth law of thermodynamics. Okay.
Okay.
That's so weird. Yeah. What about digital thermometer? Okay. So the digital thermometer actually is just using it's called it's just the conversion of, you need to do there must be some system that can make some connections with the real system that you want to make a measurement with. And then the digital one, you just have like a maybe some converter that converts from the analog signal, which is the temperature, into some digital signal, and that's all. And then you have just like, LCD screen on top. That's all. Yeah, but temperature is still temperature. Yeah, but it's just the way that you display them. You want to display them in terms of, just the regular thermometer, or you want to do digital. Yeah. All right, that's a good question actually. Yeah. All right, cool. So that's done. All right, that's not much to it. That's the zeroth law of thermodynamics, but that's talking about thermal contact and thermal equilibrium and talking about temperature. Okay. Now, when we want to use a scale, it turns out, okay, you have a couple of scales that's still in use at this point, but the main scale that we use in our everyday lives probably will be Celsius scale. So that's the one that we're using, okay? And in US, United States, they're still using Fahrenheit, maybe, okay, that's still there. But the one that we really need in science its absolute temperature scale. Okay, so this is what we need. And I'm not gonna bore you guys with this. Like this is like a historic experiment. But what they do is they're trying to measure the relationship between the gas pressure and the temperature. And to their surprises, it turns out whatever gases that they tried, for example, they have like three gases: gas one, gas two, gas number three. And when they try to plot the relationship between the pressure and temperature, they all leading to one single point. Okay, so that means it seems like there is a single temperature that's eventually all gases in this universe won't apply any pressure to the walls whatsoever. All right, so that is the point that they expect that, okay, that will be the point where nothing is or not going to move anymore. So that's why they named this one an absolute temperature scale. Okay, but starting from this point, that is fine. It looks like, you have some experiments and all this stuff. But I think maybe the easiest approach is this. Let me give like some blank space over here. Let me ask you this, guys. Imagine if you guys are just like a super simple particle in the universe. Nothing. Just like a dot. You can think of it like you could be like an electron, or you could be like a proton. I mean, just some simple particle, right? And you just like left alone in the universe. Yeah. What do you do? What do you do? You are like a single particle in the universe, and universe is like dark, blank. There's nothing. There's nothing to interact with. You don't have anything at all. Nothing. That nothingness there, that is 0 Kelvin. Does that make sense to you? When you have nothing, you have no movement. You have nothing. That means you don't have any energy. You don't have anything. That's where the absolute temperature means. Because now we understand briefly that now temperature means energy. Now here comes the thing. If somehow I can give this particle some energy, all right, by lighting some fire doesn't make sense because I shouldn't be able to do that in space. Yeah. But let's say I shine some laser light on it, maybe, bam, whatever. So let's say I give this some energy. Yeah. So I somehow can transfer some energy to this particle. What do you think this particle will do? What do you think? If somehow I can. Yeah, very good. It has to move because you don't have anything else to do. So it can move. Once it moves, it has some velocity. Yeah. Once it has velocity, of course, you can get down to 1/2 k mv squared. Sorry. Here we go. There you go. You can get to the 1/2 mv squared, and then eventually you gain some kinetic energy. And that's the gain of the energy induced the increase in temperature. Does that make sense? All right. So what I'm trying to show you right here is just taking you to the idea of temperature is pretty much the same thing as energy. That's it. So absolute temperature is just saying that the reason it has to be absolute because, of course, 1/2 mv squared, that's absolute. You can always calculate kinetic energy from velocity or the speed. That's for sure. There's no relative. There's nothing. It's a number that you can calculate. So what it means is when you talk about the 0th absolute temperature, it means that is a point where you don't have any energy at all. Cool. All right. There's a question comes in. Does this tie to the fact that energy is heat? Wait for it. All right. Very good questions. And that is the one that I'm trying to get to. All right. Does that energy means heat or not? It will be revealed today. Yeah.
Okay.
Well, it's not that exciting. All right. But anyway, I'll try to make it exciting. Okay. Anyway, so my point is now, I hope you start to see the relationship or the connection between the two. They are pretty much the same thing. Temperature means energy. For sure. Nothing else. Yeah. 0 K, that means 0 absolute temperature. That means no energy. Even though I'm just saying right now, spoiler alert here. Yeah. This is a third law of thermodynamics, says the 0th absolute 0 temperature is an unattainable temperature in this universe. There's nothing in this universe that eventually can give you 0K. When I say K, keep talking about the K, the K, the K. It's just the unit for the absolute temperature scale, and that is Kelvin right here. So that means in this universe, 0K or 0 Kelvin is not possible. You cannot get down to 0K. All right. Forget about it. All right. And you can sort of like answer this one using quantum physics or whatever. All right. We'll talk about that later. But that's the whole thing. That you can get very close, but not at absolute zero. Cool. So with that, it means we're going to use a lot of absolute scale. And of course, because we use a lot of Celsius scale, so the conversion between the two is going to be very, very useful. So the way that you can connect between the two is very simple. If you measure the temperature in Celsius, you just add 273 approximately. All right, you can be accurate, a little bit more accurate by using 0.15 if you want. But if not, 273 is good enough. Just add that 273 on top of the Celsius reading, then you get the Kelvin scale temperature. All right, cool. So for example, water boils at 100 degrees Celsius. So that will be the same thing as at 373 Kelvin, on and on. All right. And I put like a quick note over here that 0K is an unreachable point, and that is according to third law of thermodynamics. All right. Cool. But now, just before we move on, one thing that you need to know, because the relationship between the Celsius and Kelvin are simply just a constant summation, you just add 273 to it. So if I'm asking you about the change, what do you think will happen? All right, Marjan. So it means the scaling, the resolution of the scaling between these two scales are exactly the same. So that what I'm saying is, if you change temperature in Celsius by 1 degree, it will be exactly the same as you change the temperature in Kelvin scale. Does that make sense? And these two are exactly the same. So one temperature change in Celsius is going to be exactly the same 1 degree change in Kelvin. That's nice. That's nice thing about this one. Okay. So they are just shift. Think of it like a shifting, right? You just shift by 273 to get to the other one. So if you want to talk about the change, the difference, you can talk in any, not anywhere. You can talk in both units. They are having the same change. Cool. All right. So that's so you know, because we will have equation or expression that you only care about the change. So if you talk about just the change of the temperature, you can work in any unit you like, right? They're having the same, amount of change. All right, nice. Okay, keep going. So far, so good. All right, so the Fahrenheit, probably we're not gonna need to use it. All right, but for those of you that are familiar with United States sort of like units, all right, but it's so hard to use from time to time if you're not using it every day. But if you want to convert between Celsius and Fahrenheit, the equation is right there. Okay. But one thing is kind of fun to know is at 40 below, at the negative 40 degree, that's when the reading between the Fahrenheit scales and Celsius scale reading at the same numbers. So at 40 below. Negative 40 Celsius is the same as negative 40 Fahrenheit. And it's pretty cold right there.
Okay.
All right. So almost there. I think the coldest that I can get to, I think it's negative 35. I think maybe that's the coldest that I have ever experienced. Okay. Yeah, 40 below is never. All right. Anyway, okay, here we go. So I'll give you the scale in Kelvin, just so you see that the span of the temperature is huge. Like for example, over here, the lowest that physicists can achieve to get down is not -7 anymore. It's 10 to the -9 or even 10 to the -10. So I think this is outdated a little bit, but I think we can go to like a sub nano Kelvin. That's where we can do. And of course, we're not going to use any refrigerator or anything anymore. But it's sort of like, it's not like a big system that can get down to that low. But the thing is, it's just a system that you stop their movement, because now we understand that temperature is just the kinetic energy. So if you somehow can stop the movement of the atoms or molecules, that's when you get a super, super low temperature. All right. So that's why you might have heard of like a word saying like laser cooling. You cool stuff by shining the laser light on it. But the laser is not, maybe at first glance you would think like, hey, laser is supposed to heat things up. But if you look at the atomic level or molecular level, you can use the laser to stabilize the molecules or the particle, so it will stop movement. So when it stops moving, that's when you get a very, very low temperature. Okay, so that's what it means by laser cooling there. All right, so that's super low. And then liquid helium is the one that has like a single digit temperature. It could be like, only like 2, 3 Kelvin. That's when helium gas turn into liquid helium. And then the one that you maybe, you can find some liquid nitrogen ice cream and stuff, that is about 77 Kelvin. So that's somewhere around there. Okay. And now we talk about everyday lives. Now we talk about like, 2, 3, 400 Kelvin. That's when you talking about water freezes, copper melts about maybe 700 Celsius, or everything somewhere about hundreds of Kelvin. That's when your life is around. And then when you move up to like the sun, you have like a corona, the things that have some activity on the sun. That's already a million Kelvin. All right. And inside the sun, when you have like nuclear fission and things going on, there's a nuclear activity inside. That's now about 10 million. And then if you look at the center of the hydrogen bomb in the nuclear bomb and other stuff, now it can go up to 100 of millions Kelvin. All right. So as you can see, the order of magnitude of temperature is so super huge. You're coming from close to zero all the way to 10 to the 8, 10 to the 9, all this stuff. All right. So one thing that we can learn about this relationship between the temperature and physical stuff is, because now we know temperature means kinetic energy, but the kinetic energy means the movements. So think about it. So that means somehow if you can increase the temperature of something, then that thing means inside that thing supposed to have more movements, right? So what you can imagine is if you get into a room with your friends, in your classroom and stuff, and then let's say you standing, maybe the room is packed. Okay, you guys like shoulder to shoulder packed and everything, and then suddenly I just like turn off the AC, turn off the air conditioner. All right, so it means the room is gonna get hotter and hotter, of course, and then you get uncomfortable. It's like, okay, man, can you move away from me a little bit? Get some air and all this stuff. So you guys sort of like uneasy because you're getting hotter. Sort of like, okay, the room is getting higher in temperature, so you want to move a little bit more and all this stuff. Like, hey, can you just stay away from me? And on and on. So that's my analogy to the molecular movement. So I don't know, does it work or not? But the idea is this. So same thing happens to the molecules. So if you give it some temperature change, so when the temperature rises, these molecules tend to move more. So when they have more movement, so the separation between them on average seem to be larger as well. Yeah, because they're going to stay further apart. So that's why at the end, as the collective properties, so when you zoom out, right, when you zoom it in, you might just, okay, this is tiny, tiny, tiny movement. But when you have all those collective movements and then you zoom out, then you might be able to find out that there is some expansion that you can notice in the macroscopic level. Sounds good? All right. So this means what I'm saying is things seem to expand when it gets hotter. And when I say hotter, it means higher in temperature. And things seems to shrink down when it gets colder or temperature is lower. We call this thermal expansion. Cool? All right. So that's what we're trying to do here. And now this is the first test of physics 102. So we're going to do some calculation right here. So what we're trying to do here is this. We're going to need some equation, of course. All right. And the equation that we need is just the equation that will allow us to calculate the change, okay, that happens to the physical dimension of the object. So what we're going to do is we're going to look at the change in the length. Okay. So let's say that you have a piece of some material that have a starting length of L0 right there. and then somehow you warm it up. Okay, and just forget about heat at this point, but let's say you heat it up, you give it some energy, so temperature is higher. So let's say at higher temperature, in comparison to the lower temperature, the temperature change is delta T. So the change in temperature is delta T. So at the end, you will end up with a larger or the longer piece of this object. So let's say that the extension that happened is delta L. So what we can expect to sort of write down the expression of the delta L is this. You say, hey, Dan, delta L supposed to depends on what? For sure, depends on the temperature change. The greater the change, the greater the delta L. That's one thing. The second thing that could happen is, right, what is the length initially? What is your initial length? If you come up with like a long piece of stuff and then you extend even further, you're going to get more, the change of the length will get higher. So it depends on the original length of that piece of object. And the last one, of course, what type of material that you bring in, right? Because some material expands easily, some material might not want to expand much, on and on. So you might have some intrinsic ability of that material to respond to the change of the temperature. Does that make sense? All right. So, well, when you see these three, okay, I can put these three into an equation. Why not? So what I can write down is the change of the length can be written as the alpha, that's ability to expand the original length, and the change in temperature. Simple as that.
Okay.
There's a question coming, but very good question right there. Wow, you guys, it's like you know me. All right, you got me there. Here we go. Well, all right. Spoiler alert here.
Okay.
Yeah, not all of the material behave this way. Very good. Good catch right there. Perfect. Because like water, you guys know that water has the highest density around 4 degrees Celsius. So that means if you start your whatever observation at 4, so it's going to expand no matter what. You're going to higher or you're going to lower temperature, they're both expanding. Right. So that is actually my key point. Thank you for the question. My key point is this. You look at this equation, what do you feel? What do you feel? Well, Adan, this is like kind of lame. Because you just say, hey, delta L depends on the change of the temperature. The delta L supposed to depends on the initial length. The delta L supposed to be depending on the type of material that you bring in. I'm going to just put them in a product and I'm done. You guys see what I'm trying to express here? It's not like Newton's law, sigma F equal to ma. That was like an equation of like the universe has to follow, right? But this one is just an equation that allow you to explain the expansion phenomena easily. When I say easily, is because this is a linear equation. You guys see what I'm saying here? So this is not like an equation of the universe. This is just an equation that allow you to explain the linear expansion. There is the linear term in here. So in reality, some material might not expand linearly. Who knows? It can depend on alpha square. It could depend on delta T cube. Who knows? Or just like your friend just pointed out, some material doesn't even want to follow at all. It can expand on both ways. I mean, you can increase or decrease the temperature. I'm just going to expand both sides. Cool. So just want to remind you that whatever we are doing over here, this is an expression of an approximation. This is not as highly regarded as like sigma F equal to ma level of equation. You guys, you see what I'm saying here? Yeah. So don't take this equation too seriously. This one is more like an engineering question. It's like, okay, I have some things that expanded. I want to have some mathematical expression to explain this. And I'm just going to make my life a little bit easier. I'm just going to stick with linear term. And that's it. I'm done.
Okay.
Cool. All right. So this is the reason I want to point this out, because I want you to feel a little bit comfortable dealing with this equation as like an approximation. Don't think of this one as like, Ajan, this is going to be accurate down to like the 5th digit accuracy or no. It's purely approximation. Cool. And I will show you even more. Why does it so? Okay, guys, look at this one. The alpha that we introduced, it has a name. Let's call it the coefficient of linear expansion. So think of it like just a coefficient that's intrinsic to some particular material. Okay, so that's all. So this table give you the value of the alpha for common material, and mostly they are pretty much like metal, aluminum, copper, lead, steel, right? And you have some glass there, you have some concrete there. Cool. So the question is, can the alpha for ice be negative if it goes opposite way? Yeah, you can. Eventually, yes, you can define the negative coefficients, but you will see that we don't want to go that far anymore because we don't have like a general equation that describe all the expansion in all types of materials. Okay, so that means you just have to go case by case, and then you just do the model. Just assume that this one follow linear law, the next one might follow like quadratic terms, the next one might have like a cubic term, on and on. All right, so that's why I'm saying don't be too serious about this equation in terms of the accuracy. Cool. All right, so one thing that you can notice from this table right here is, if you look at, here we go, steel and concrete, see that they have a very close value of the alpha. And that makes sense because when you're building like a building, a skyscraper or whatever, then you have like a concrete with the steel reinforced, right? So you have concrete and steel together in one piece of maybe your wall or whatever your building structure and everything. So you want them to expand and contract at the same rate during the daytime and the nighttime. So if you don't have the same value of the alpha, of course, steel, if it expands too much, then it's going to crack the concrete or whatever, and you're going to have some nasty thing going on. So this is a reason why, I mean, from the engineering point of view, and from, of course, everything has to coincide, then the steel and concrete has to come with the same alpha, yeah, for them to be able to expand and contract at the same rate at all time. Okay. All right. So that's kind of like cool. And one thing that's, well, I think this is a classic photo that showcased the construction that sort of like forgot to take into account the ability of the metal to expand. But one thing that still sort of like puzzles me until today is, I'm not so sure why this project has already been completed before they can observe this phenomena. I don't know why. It's like maybe global warming, or during the construction the temperature is just so steady, so they don't have any problems about the expansion or whatever. So it's like, it's there is like, I don't know, the train is already running. So it means it must be in use for a while before this problem just creep in. So not so sure why. Yeah, they should have already spotted this like during the construction time, but it didn't happen. Not so sure. All right, guys, here we go. Now, you guys probably wondering, Martin, wait a second. This is like a block of stuff. Why you care only in particular one dimension, which is the length? Well, Martin, what happened to the height? And what happened to the width? Well, Martin, you don't care? I care. And actually, they have to expand in all directions. That is true. So what we have to, I mean, what we can do next is, let's talk about the volume expansion. Okay, not just only just the length expansion anymore, but talk about the volume. So, well, okay, you want the volume, I'll give you the volume. The change in the volume equal to same structure. Can you see that? There is some coefficient of volume expansion. So let's name it like beta. And of course, it depends on the initial volume at first. And then, of course, it has to be depending on the temperature change. And now you start wondering, Ajahn, why equation look exactly the same? Wondering? Well, then why not, if it has like, it's the length times width times height, then there should have like a delta cube or something in this equation. But how come they all look linear again? And here comes the answer, guys. All right. And I'm going to show you some mathematics here. So we're learning physics, so we need some math anyway. Here we go, guys. So let's follow me this one if you can. This is the volume that we want. Of course, the volume is the length times the width times the height. No big deal. Now you warm things up, temperature rises, you have a new temperature. So your new temperature is now added delta T to it. So that's your new temperature. Of course, the length, the width, and the height will extend linearly in each dimension. So we already learned how to calculate the delta L, the change in the length. So all you have to do is the new length is going to be the original length L plus the delta L, the increase in length, right? So it's going to be alpha L delta T. Cool. That's the new L.
Okay.
And then you do the same thing with the width. You start with the W, and then you just calculate the delta W, the change in the width. It's going to be the alpha, original width, and the change in the temperature. Cool. Same thing happens to the height. The final height will be the original height times the change in the height, alpha H delta T. Now, in reality, you just have to multiply these three terms together. And because they all sharing the same common factor of 1 plus, if you pull L out here, let me do color code here. If you pull L out, sorry, wrong. Here you go. You will be left with 1 plus alpha delta T. If you pull W out, you will be left with 1 plus alpha delta T. If you pull H out, you will be left with the same 1 plus alpha delta T. So that means you have 3 of the 1 plus alpha delta 3 cube right there. And here comes my point. This equation is just an approximation. And we don't want to deal with the cubic terms all the time. Doing the cubic term is just annoying, right? And it takes computational times. So we're just going to approximate this. So I'm just asking you guys for fun. You guys know this expression right here? Does it, give you any clue? 1 plus x to the n approximately equal to 1 plus nx. If not, that's okay. Just for fun, remember this complete square term, 1 plus x square is หน้ากำลังสองบวกสองหน้าหลังบวกหลังกำลังสอง yeah?
Okay.
So it's going to be 1 plus 2x plus x squared. Now, if you do the cubic term, it's going to be 1 plus 3x plus 3x plus x cubed. There you go. Does that make sense? And if you do one more, I can do one more. 1 plus x to the 4th, if you like. So it's going to be 1 plus 4x plus 6x squared plus 4x cubed plus x to the 4th. On and on and on. So you know how to deal with this, the exponent of raised to the power, whatever, 1 plus x. Here comes the thing. If these x's is small, think of it like small, like how small. It could be like really 0.01 or 0.001, on and on. You will see that the smaller the x gets, those higher order term will get less and less significance. Does that make sense? And this is the reason why this is at the point where, okay, if x is not big, I'm just going to forget about the higher order term. I don't want it. We call this the linearization. You try to take things to be as linear as possible, because for those of you that come from computer science and all the stuff, you guys know that linear equation is so easy to solve. Linear calculation is, doesn't take a lot of CPU time, on and on. It's just, addition, that you don't have any, multiplication or power and stuff to do. So it saves a lot of time. So that's the whole idea. So this is the reason why 1 plus x to the n, now you can see n is just showing up right there. See, n, as the first term, the coefficient of the linear term is just n. So that's why we can approximate 1 plus x to the n to be about 1 plus nx. And that's what you see over here. I can approximate that cubic term and put them simply just saying that it's just 1 plus 3 alpha delta t. Here we go. 3 alpha delta t. 1 is just showing up right there. And I am done. Cool?
Okay. Okay.
Nice. And one thing that you can notice right here is, well, oh, Adan, if you do this, that means what you are looking at here, this is LWH, that is your original volume. LWH, that's your original volume. They have 3 alpha shows up right here. But whatever you're seeing right now and on the back here, this is just the change in the volume that you are looking for. So that's why we can draw like a quick conclusion over here is the beta that we introduce up here for the material that expand equally in all direction. When I say equal in all direction means the length, the width, the height, they're all expanding at the same rate, alpha. The beta is going to be just triple of the alpha. That's it.
Okay.
Cool? Not bad. But this is sort of like confirm my point. Just want to confirm to you guys that this equation is just an approximation. It's not like law of the universe or anything. So for those of you that have like Adan, I have high speed computer. I don't have to do this approximation. I can plug it into my code and then have computer calculate everything. You can just stop right here and then you can do the calculation of the cubic function. You have a higher and more accurate result actually, right? But just for simplicity, we're just gonna stick with the linear term, and we are done here.
Okay.
Cool. เฮ้ยอาจารย์พูดรู้เรื่องไหมเนี่ยพอได้ไหม Does that make sense? All right. Okay. Cool. All right. But just to confirm and just sort of having fun seeing each other for the first time here, I have another approach to you guys. So instead of doing all those approximation or cubic terms and do the linearization and all this stuff, I can start from here. Let's assume that you have a cube of length L. So the volume of that cube is going to be L cubed. And now I'm doing derivative a little bit. So you guys do remember this one, yeah?
Okay.
I'm doing the differential change, the change of the volume. And now I do a little bit of like a chain rule over here. So I can do, hey, what is the change of the volume with respect to the length? And then I might just multiply by the differential of the length again. You guys with me? So it's just like what I'm doing is just I'm doing like dv by dl. And it's just dv by dl is equal to dv by dl. And dv is just dv by dl. And then it's just like I just move dl to the right hand side and express the dl as a differential change. Same thing. Okay. And then with this, then I can do the derivative. Derivative of v is just l cubed. So the derivative is 3l squared. And now what you can do is, well, this is just the length change. So I already saw that the delta L is alpha L naught delta T, right? If I want just like a super, super, super tiny change, differential change, everything like going, approaching zero and everything. So I can turn this equation and write this one as a change in the length. It's going to be the alpha, stay the same. The length itself, because it's differential. So the length at that point is going to be your initial length. And then the temperature will probably change just a bit. Let's call it the dt. And that's why I can turn this dl into alpha L dt. And then now I can move that alpha L, plug it back into the front. And the L cube is just the volume. And then the 3 alpha show up as the beta again. And you
Okay. Okay.
Cool. All right. So, no matter what you do, it's just approximation. It's not real here. Okay, don't be too serious about this equation. All right. So we're happy with just the linear term. So with the understanding of what behind the scene that you're doing with the math, you're doing with the approximation. So if I'm asking you what should happen for a sheet of material, so it's just 2 dimension. If you have like a piece of stuff that has only like the width and the length, so you can guess, but Ajahn, the expansion in terms of the area expansion has to be 2 alpha. Does that make sense now? So you can actually write the equation for the change of the area to be 2 alpha original area times the change in the temperature, and you are done.
Okay.
So I hope by understanding the behind the scenes mathematics or behind the scenes approximation. I mean, 2 alpha pretty much come naturally. It's just okay, all right. I mean, you have 3 dimensional stuff, it's 3 alpha. You can name it beta if you like. If you have 2 dimension, it's going to be 2 alpha because it's only have the width and the length. And if you only care about single dimension, okay, you just have alpha, and then you only care about the length change, and you're done. Nice. Okay. All right. So not too bad. I think that's a very good introduction of, I don't know. I mean, what's coming is much more than this.
Okay.
All right. So this table will give you a list of coefficient of volume expansion, and just to be like contrast to what you already had before for the metal or solid stuff, you already had the alpha. So over here, the beta usually they will use for liquid or gas, maybe. Yeah, because I mean, for gas, you won't be talking about the length of the gas. You'll probably be talking about the volume of the gas. Same thing with the liquid, right? You're not going to talk about, but the liquid is sort of like sometimes you might be able to measure the width, the length, the height of your container on and on. But anyway, so you understand the relationship between the alpha and the beta, so it shouldn't be a problem. Cool. All right. There is some application that you can do with this thermal expansion, but this one is less and less uh, important in your life because this one is called thermostats. So it's a temperature controller. It's a hardware controller actually. It's still very useful in the place where the electronics might not work so well. Maybe like in the furnace or in like a super hot or super cold temperature or something like that. So this one use the bimetallic strip. So you bring in 2 types of metal, like over here in the figure, you have steel and brass. And it turns out, of course, you guys know the alpha of steel and alpha of brass will be different. So that means when you go through some temperature change, these two will expand at the different rates. For in this case, for example, brass expand more than steel. So in this case, so you're gonna get some bending. So when you get some bending over here, you can put this into a mechanical stuff that acts like a switch. This is cool. All right. So that means this is how it works. So when things get hotter, so you can, in this case, you take the switch to be off. So you close the switch when it's hotter, and that's when you use it as a temperature control. All right. And when it's cool down, you switch down again. When it's hot, or you can do the opposite way, up to you. All right. But the idea is this is how you can control the temperature using the thermal expansion property of different material and put them into a bimetallic strip. That's how it works. All right. But of course, nowadays we all use electronics control, even like some AI or whatever. Yeah, so this is kind of cute, but not anymore. Okay, cool. All right, and this is already discussed. Water is an exception. It's a very big exception actually. So we won't be talking about water so much. Right? We know it. There's so many other material that does not follow our equations at all, like some type of like exotic polymer or exotic ceramic, or some weird stuff, weird mixture of stuff. So right, that's what it is. Okay, guys, so let's finalize today's lecture with a couple of exercises, shall we? And then we just uh, call it done for today, and then we'll see each other again on Wednesday. All right, so I have a quick question over here. Two spheres are made of the same metal, have the same radius, but one is hollow and the other is solid. The spheres are taken through the same temperature increase. What or which one will expand more? Whoa. So you have one sphere that's kind of hollow in here, and there's another one that's solid. You raise them through the same temperature change. Which one should expand more? All right. If you like this kind of question, I have another question for you. If you have a piece of metal with a hole, maybe a rectangular hole in the middle, and when I make this piece of metal change in temperature, delta T, what should happen to the hole? Something like that, right? This is the kind of question is sort of like same class of question. So let's do on the left first, guys. Do you think the hollow sphere or just a solid sphere which one will expand more? What do you think? Based on our discussion, though, right? Don't think too much. All right, a little bit of motivation here. Solid expands more. Okay, okay. Solid. Okay, everyone seems to agree with solid. Okay, why do you think solid seems to expand more? Because it feels like it has more stuff in it, I guess, right? Intuitively, it seems right. But then, what I would like to argue is this: let's say if I am one of the atoms that composes that solid, maybe I'm just one atom in there. Here, okay. And don't forget, this atom is going to be like nanoscale. It's going to be like 10 to the negative 9, 10 to the negative 10 or whatever, super duper small, right? Yeah, yeah, very good. All right. So, all right. The idea for you seems like, yeah, well, Ajahn, the hollow one seems to be able to expand inward, right? And the outer one is going to expand outward. So it's overall, then it's not going to expand as much. But the solid, there's no inward, it's only expand outward. But my argument is this: if I am this molecule over here, I'm gonna have my neighbor around me, of course, my neighbor, my neighbor, my neighbor, my neighbor, right? I'm not gonna be able to tell if I am inside a hollow solid or a solid, I mean, a hollow sphere or a solid sphere, right? So what I'm doing locally, I'm just gonna like, hey, get out of my way, right? Stay out. Don't get too close. That's all I can do, right? At the nanoscale. So locally, the situation between solid and hollow wouldn't do anything different. I would do exactly the same thing no matter it's a hollow sphere or it's a solid sphere. Does that make sense to you guys? Plus, if you argue that, Bajan, this can expand inward, that's kind of weird. Because if you want this whole thing to expand inward, it means all of those molecules that is inside the inner edge over here must have an ability to pull the rest of the molecule inward. Imagine that. Like, hey guys, I am like, on the edge over here, and let's work together and then let's pull the rest of the sphere inward. There you go. No, that's not possible. Does that make sense? Right? So there's no expand inward. It cannot be done. Even though logically it seems like it should be, but it's not. So my idea is this. So this is the reason why I asked you this particular question along with this. What do you think will happen to this uh, rectangle in the middle, the hole in the middle? Do you think it's going to expand or it's going to shrink? So if you use the idea that it can expand inward, you would say that this hole over here is going to shrink down. But the answer is no. When you talk about expansion, it will expand no matter what. So that means at the end, the hole will get bigger and the piece of the whole thing will get bigger as well. So you can think of this expansion like a Photoshop. You're doing the enlargement. If you want to go like 5%, 10%, everything will get enlarged altogether. All right. So one way that you can imagine that, hey, my argument has to be true is, well, hey, instead of having a hole, if I'm not having a hole, if I only have a mark, say on here, just like, it's not a hole. It's just like my mark writing as like a rectangle. And I'm asking you, hey, I warm this thing up. What happened to my dash rectangular structure over there? Everyone will answer expand. Everything will expand out. But when I cut as a whole, it's going to change into contract, getting shrink, getting smaller. No, that's not possible. It's going to expand no matter what. Does that make sense to you guys? So my conclusion is this: no matter what shape of the material is going to be, okay, you can think of this one as an enlargement of the whole piece. Think of it like doing a Photoshop and then you enlarge everything. All right. And this whole thing, all right, if you dig down deep into a super, super duper detail, of course, they're not going to be exactly the same, but up to a linear term that we have been approximated with. Perfect. these two are just expanding in every dimension, every direction equally. Okay, guys? Does that my explanation seems to make sense? Yeah. Okay. So don't think too much about the whole, the hollow or whatever. If you're gonna get expansion, they're gonna expand overall because of the concept of the expansion. It's just the separation of the distance between molecules. Okay, molecule cannot detect is it gonna be hollow or solid, so it won't be that much difference. All right, guys. And the last one before we leave. All right. So let's do some simple calculation. This one is a plug and play, but just to make sure that you know how to do it. Aluminum tube is 3 meters long at 20 degrees C. What is going to be the length when it's at 40 and at 0? So this one just to confirm that you can have temperature change in the up direction and in the down direction as well. So in the up direction over here means the delta T is positive 20. Does that make sense? Okay, and the down here, it's mean the delta T, it's just negative 20 degrees Celsius. So don't worry about substituting the positive or negative. When the delta L, the change of the length is negative, mean it's just shrinking. It's shrinking down. That's fine. So they want the new length. So what I'm gonna do is, okay, let me do part A. So the new length, let me put the prime on it. It's gonna be the original length plus the delta L. And that will be the L naught plus alpha L naught delta T. So in some textbook, they will ask you to remember or sort of like note this equation right here. That is fine. Okay, some textbook, they talk about the new length altogether, not just the change in the length. So they put the expression in the formula in this form. And the rest of this one is just plug in the number and then you're done. So you just find out what is the alpha for the aluminum, and the delta T over here is just positive 20 degrees Celsius, and you done. Cool. All right, is that easy enough? And for part B, you're doing exactly the same. The new length, let me put double prime there just to distinguish from part A. It's just going to be the original length 1 plus alpha delta T. And don't be afraid, this one L naught, okay, let me put the number in here for you guys. It's 3 meters. 1 plus alpha of the aluminum, you can look it up in the table or in the Google, and then you just substitute negative 20 in there, and you're good to go. You are done.
Okay.
Cool. So that's what it is. All right, guys, I think what I'm going to do is I'm just going to leave it here, and next time on Wednesday, I'm going to just work on a couple more exercise here as a review of what we just already did, and then we move on to the next topic. Sounds cool? All right, guys. So thank you for sticking around, and I will see you guys on Wednesday. All right. Do we have any before class reading material? You can read. You can download that handout, I think, and you can do the handout reading. And if you want to read more, just go to the reference text, and you can read stuff there. Yep, definitely. Oh, okay, definitely. I can once I complete this handout, then I can upload this written handout as well. Yeah, no problem, guys. It will be up there on the classroom as well. Cool, no problem. All right, just ask me anything. I'll do it. All right, guys. Thank you so much, and I'll see you guys on Wednesday. And every week I will put the Zoom link on the Google Classroom. All right, so you can check out the link there. All right, guys. Take care. Stay safe. I'll see you guys on Wednesday. Bye-bye. Thank you ครับ บ๊ายบายสวัสดีครับ
ครับ